Hello everyone, this is Professor Keen. In the last few lectures, we, along with Galileo, have been thinking about the relationship between the frequency of a vibrating string and the pitch of the noise that it makes. And specifically in the last lecture, we talked about how if you tighten the string in a certain way, or if you make it heavier in a certain way, or if you change the length of the string, you can change the frequency and hence the pitch. One of the main questions that Galileo is trying to address in this text is, let me write it down here. Here's the question. Why do certain combinations of notes, so why do certain combinations of notes sound good together or sound pleasing to the ear, while other combinations sound bad? You're probably familiar with this. If you pick out random two notes on the piano and strike them together, or three notes and strike them together, it's not going to sound very good. But if you pick out particular combinations, they sound very good together. So what is the reason for that? That's the question that Galileo is addressing. And in particular, what Galileo thinks, and this is right around page 64, is he talks about this in terms of whether the frequencies are commensurate or not. So for example, if you were to take two notes that are separated by an octave, if it's an octave, then the ratio of the frequencies is 2 to 1. And he says this is pleasing to the ear because these numbers are commensurate numbers. That is, for every two vibrations of one string, there's one vibration of the other. Another example of a pleasing frequency is a fifth. There you have a ratio of 3 to 2. And once again, this is pleasing to the ear. For every three vibrations of one string, there are two vibrations of the other. Another example is a fourth. The fourth sounds good because there's a 4 to 3 ratio. Once again, it's pleasing. All right. As this number gets larger and larger, the sound becomes less and less pleasing, he argues. So if I have this correct, I think it's called a second, has a ratio of 9 to 8. That is, it takes 9 vibrations of one string until the other one goes through 8 vibrations. This is kind of a borderline case where it's starting to feel dissonant. So up in this direction, you have consonant notes. And in this direction, they become more and more dissonant. That is unpleasing to the ear. Because he says somehow when your ear can detect a pattern between the vibrations produced by one string in the air and the vibrations produced by the other string in the air, your ear detects that pattern and finds some kind of pleasure in it. And the longer that your ear is held in suspense until the vibrations line up again, so to speak, the more dissonant the interval. Okay, so he says that, I'll write that down, the longer the ear is held in suspense before the vibrations line up again. I'll say more about this in a moment. Before the vibration lines up again, so to speak, the more dissonant the note. So in order to understand this, I think it would help to think about pendulums, and this is why this chapter is called The Relationship Between Pendular Motion and Harmony. So let me draw a picture here. Let's suppose we have a pendulum, and this pendulum is just the right length that if you pull it back and let it swing back and forth, it swings back and forth once in 1 second. So the frequency of this pendulum is 1. It takes 1 second to swing back and forth, so it's a frequency of 1 hertz. If I were to, let me make this orange here. So this is the frequency. Frequency 1 is 1, and the angle here. So if we were to plot the angle of this as a function of time, it starts out let's suppose you started out right down here and you punch it so it swings up and starts swinging back and forth. Well, when you do that, if you were to plot the angle versus time, what would you get? You would get a plot that looks something like this. In 1 second, so this is in seconds, in 1 second, let me see if I can draw this nicely, the angle will go up, reach a maximum, then swing back through the bottom, reach a maximum on the other side, and then come back like this. So that's a plot of the angle versus time of this pendulum. Now let's suppose that we have another pendulum, and we make this pendulum a bit shorter. And so it has a higher frequency, okay? And we make it so that the frequency of this pendulum 2 is 2. That means it swings back and forth 2 times per second. So if I were to plot the angle as a function of time, once again in seconds, and I would say that it swings back and forth 2 times in a second because of the length. So what's going to happen is it's going to swing up. Whoops, let me go back here. So it's going to go up and down. That's 1 vibration in a half a second. And then up and down, and that's 2 vibrations in 1 second. So notice if you compare these two swinging pendulum, if they both start out at the same position, right here, it takes 1 full second for them to line up again. So they're going to, this one's going through 1 oscillation here, but this one's going up while this one's going back. And so when you get to this point right here, then they will have lined up again, and now they're both going to start off onto their next set of vibrations. So that's what we mean by a 2-to-1 ratio. So when you watch these swinging back and forth, you would see this one swing back and forth once, and this one swing back and forth twice in the same time period, and your eye would detect that pattern, and you would perhaps be a bit hypnotized by this, thinking it looks beautiful to have these two pendula having this relationship between their frequencies. Galileo argues that your ear does the same kind of thing for sound vibrations. If the sound vibrations have these nice ratios like 2-to-1, then your ear detects that ratio and thinks it to be pleasing. And we might do one more example. If we make an even shorter pendulum, this is getting a little bit short, but let's suppose we have this one. The frequency of pendulum 3 is 3. All right, so we plot like this, and this is the angle, once again, of this pendulum. It swings back and forth 3 times in a second. So once, twice, 3 times, right? So it takes 3 vibrations for them to line up, for this one to line up with this one, and for this one to line up with this one. But nonetheless, your eye will sort of detect this pattern. The more vibrations it takes for them to line up, the more complex it's going to look, and the more, I guess, discordant it will appear to your eye, and likewise, the more discordant the music will sound to your ear if this is a vibrating guitar string instead of a vibrating pendulum. You might think about an extreme case that would be completely dissonant. That is, if these numbers were incommensurate, if you had pendulum swinging back and forth and another one swinging back and forth, so that you could not form a ratio of integers that describes this. Those would be called an incommensurate set of frequencies. And how would you do that? Well, let's think about guitar strings for a minute. Let's suppose we had, and Galileo gives this example, let's suppose you have a wooden board, and this wooden board, so here's the wooden board, you'll see where I'm going with this in a minute, and we put 4 nails into it in the form of a perfect square. And then we stretch a string across from here to here, and that string has length L. And we stretch another string across right here, and that one has a length L as well. And let's suppose we get the tensions exactly the same and the mass is exactly the same. Well, we'll call this L1 and L2. If you pluck those 2 strings, the frequency of string 1 will be exactly equal to the frequency of string 2 because they have the same tensions, the same lengths, and the same mass per unit length, which means they have the same frequencies. They will, of course, be commensurate. They will have a nice ratio of so F2 to F1 will be a 1-to-1 ratio. Okay, but could we make an incommensurate ratio? That is, could this ratio be an irrational number? Well, the answer is yes, because if we stretch a string across this diagonal, and this would be length 3, we know that the length of the diagonal of a square is, if this is 1 and this is 1, this would be the square root of 2, which is an irrational number. Okay, so f3 compared to f1 is going to be in the same ratio as the inverse of their lengths, which is 1 over the square root of 2, or root 2 over 2. And remember that this right here is an irrational number. That means that if you pluck both these strings at the same moment, they will both start undergoing these vibrations, but if they lined up to begin with, they will never again line up with each other. They will never, the tension will never be resolved by them lining up together. This would be a set of perfectly dissonant notes, and Galileo would argue that this does not sound good together, and it has this mathematical reason for this. Okay, so there's some neat kind of relationships between mathematics and music. There's a couple of neat videos that you might want to check out that I found online. I'll make a note over here, some nice references. I'd like to put notes, I think, in writing this video, but until I figure out how to do that, I'll just tell you what they are. One of them is it's a YouTube video called Pendulum Waves. I'll probably post this on my website. Pendulum Waves starring Alan. Just look that up. And he does an experiment with pendulums of different natural frequencies, and it's kind of it's a really neat video. Pendulum Waves starring Alan. That's one video you might want to check out. And the second one, and this is tangentially related to this kind of thing, but it's kind of neat because it talks about music theory and its relationship to mathematics in terms of Led Zeppelin music. So you might want to look up another video called What Makes John Bonham such a good drummer. This is a fascinating video about the drummer John Bonham for Led Zeppelin and some of their music. So this is a really neat video. I'd highly recommend checking it out, and I think that will bring us to an end until next time.